Yogesh. Can you hear
Hi.
me?
Yeah, I can.
Okay. All right, maybe you can just say hi to our audience here.
Hello.
Can you guys hear me? Okay. All right. So I'm just going to give a quick introduction. So our speaker for today is Mr. Yogesh Kulkarni. He is the principal architect of iCertis Pune. Yogesh has spent more than 2 decades in CAD engineering research and software development. So he has a wide variety of capacities, including R&D group, and he was a site manager for one. So for the past few years, Mr. Yogesh has been fully into Python machine or deep learning, TensorFlow, and natural language processing. So on weekends, he teaches and organizes meetups, workshops in AI and data science. Okay, so for this session, Mr. Yogesh will be speaking about a case study on deep learning for geometric algorithms, Midcurve, and he will also talk about how neural networks can be applied to a dimension reduction geometric algorithm. Okay, all right, Mr. Yogesh, over to you.
Thanks, Abby. Thanks for the introduction. Let me share my screen. Ivy, can you confirm if you can see my screen? Hello. Ivy, can you confirm if you can see my screen?
Yes, we can. Go ahead.
Wonderful. Thank you. Good morning. This talk is about using deep learning for geometric algorithms. I've divided this talk into two parts. First, about what are geometric algorithms, or what is the domain. And the next part would be about deep learning, using deep learning for solving such problems. So this talk is a little different, rather very different than whatever generally talks you hear about AI, ML, or neural networks. This talk is more about problem definition or problem formulation. For a given domain, how can you formulate a problem so that it can be solved by neural networks? So I'll talk, first half of this presentation would be on the domain itself. What is the domain? So once we understand the domain, then we can see how to apply. While talking about the domain, I'll also talk about how problem is simplified. Initially, the problem is very complex, very hard. Now, basing some assumptions, it can be diluted. It can be simplified to such an extent so that we can solve it by neural network. So first, I will talk about the domain itself. Now, this domain is what is called as machine design. Not machine learning, machine design, meaning the shapes that you see created, the chair that you are sitting on, the table, how to design that, what would be its shape. And then simple idea would be, if you are sitting on a chair, it should be strong enough to take your weight, right? If you whatever 60 kg, it should take. And what should be its shape? So that is all decided in machine design. And you can see quite a few products around, including aeroplanes, cars, and then construction, and many products. These are designed so that they serve a purpose. And many a times the purpose is strength. It should take some weight, and it should not bend, it should not fall apart, it should not get destroyed by just weight. So this is the domain. Now, if you want to build a chair and see how much weight it takes, in a normal scenario, you would have to create, say, 10 chairs and put different weights on top of each and then see which one actually fails, right? But this is very time consuming. It is very expensive making 10 chairs. And in case of chairs, it's possible. But if you want to design an aeroplane, will you make 10 aeroplanes and then decide which one fails? So that's not possible. So for last few decades, 40, 50 years, things have been designed on computer. So that technology is called as CAD, computer aided design. So design shapes on computer and also analyze them on computer itself. This is called as CAE, computer aided engineering. Meaning, if you design a shape on computer, and then you can apply loads, weights, and see whether it is failing or not. So everything is done on computer now. And of course, towards end, once the computer analysis is okay, then we build some prototypes physically and then take to production. So CAD is for designing and CAE for analysis. So this is the domain I'll be talking about in this presentation for most of the part. And towards end, of course, I'll talk about how neural networks are used in this domain. Now, these shapes are very complex, right? Even on chair, if you see, there are quite a few nuts, holes, so some fillets. These are small details. So for doing analysis, we don't need these small details. So shapes are simplified. So these small details are removed. So this is what is shown in the third point. A shape is simplified before taking it to analysis. And there are many simplifications that you can do, removing holes, removing chamfers or fillets. But in some special case, actually I'll show how this works. So this is the shape. I want to see how it performs given a weight. I'll give you a slight background. You need not remember it, but this shape is discretized, meaning broken into small, simpler shapes. Okay, and then each shape is analyzed. This is called as meshing, and you can see meshing on the right-hand side. It's almost like Lego blocks. If you are preparing a shape using Lego blocks, individual Lego block is very simple, but the shape that you can create with it is very complex. So this is the background behind CAD and CAE. In case of shapes which are thin, like this, plastic shapes or sheet metal shapes, there is one simplification that you can do. You can just assume that thickness is not there. So instead of 3D Legos, 3D bricks Legos, you can have 2D Lego, meaning surface Legos, just like puzzles, jigsaw puzzles. And that shape is created. What's the use of this? Use of this is one dimension is reduced, so a lot of calculations are reduced. But the results are very equivalent. So this is very popular method in case of thin shapes because the thickness is very constant. So in case of sheet metals or plastic parts, thickness is assumed to be not there or constant, and those calculations are not done. So the problem now is, given a thin wall shape, can you find a middle shape, which is in the middle, so that we can do meshing on it. So given a shape on left, can you create a thin shape on the right so that meshing can be done? So this is the problem. Original problem was how to design shapes, chairs, tables. Now the problem is, given a 3D thin shape, how can you create a surface shape? Correct? We will go on making such assumptions and simplifications. So now the problem is, given a 3D thin shape, how can you compute a surface shape? And this surface is called as mid-surface. It's in the middle. And I'll show you a couple of diagrams how it looks. So don't worry if you cannot imagine as of now. What's the use? Instead of, if you do solid mesh, these are so many elements. But if you do surface mesh, the elements are reduced, meaning number of calculations are reduced. But this result value, as you can see in the bold, are sort of comparable. They are okay. And the time solve is half. If you do 3D blocks like thing, it takes 30 minutes for these calculations, strength analysis. But in case of shell, meaning surface meshing, it takes almost half. But very similar accuracy. So that's the advantage. So this is the problem I'm trying to solve. Given a 3D shape, how can I calculate the surface shape? Got it? This is how it looks. So now the problem is, given a 3D thin shape, I've called it solid, can you calculate the surface in the middle, called mid-surface? It's very widely used in the automobile or aerospace or any product design where sheet metals and plastics or thin walled parts are used. But you can imagine, given a shape like this, meaning say geometry of the shape like this, how to come up with this mid-surface. And it's very challenging. Research is going on for 50, 60 years, but the problem is still unsolved. So let's simplify it a little later also, because solving this is still difficult. Like this. This research of computing mid-surface is going on for decades. And many commercial packages have it. So given a shape like this, you need to create a thin surface shape like this. Okay. But even in the current software, given a shape on the left, the surface shape created is on the right. Can you see the problem? There are quite a few surfaces missing. There are gaps, and we don't want such things. We want continuous shape, right? So this is the problem people are tackling many years now. How to create a shape. Even if you don't follow this domain, just try to understand as much as you can. The real problem is little later. Okay, I'm talking about how to simplify a problem. So we cannot tolerate gaps. So my name here. So if you model a 3D shape like this, what would be its mid-surface? Can you imagine? It would be a surface shape in the middle. And ideally, it should look like this. But currently, as you can see, there are gaps. So I want a shape like this, but without gaps. So this is the current almost latest software is that too. Then what people do? People go on putting surfaces and close the gaps. So this is a manual effort which we want to avoid. If this transformation from solid to surface would have been very good, we wouldn't have to do manual corrections. Okay. This is how a commercial, for a very simple shape like this 3D shape, the 2D shape, the surface shape is not coming correct. Getting it? So this is the original problem. And I'll now simplify the problem. Okay. Current quality is this. Now, how these shapes are made, I'm taking very simple example. Say if you want to create a shape like this, typically what is done, we take up what is called as profile or a sketch, and then it is swept along a direction, swept or extruded. So you get a 3D shape like this. So what would be a mid-surface of this? Very simple. Take the same profile, yellow profile, and create a curve in the middle, right? This is a mid-curve because it's a sketch, right? And if you sweep or extrude the mid-curve, then you will get the mid-surface. So I'm trying to simplify the problem, right? So the original problem was given a 3D solid like this, how to compute a middle surface. Now we have reduced it. Because it is a sweep operation, given a yellow profile like this, how to compute the mid-curve. Isn't it equivalent? Because both are extruded or swept. So the problem is coming from 3D to 2D change from solid to surface to a curve problem. A closed curve or almost like a polygon or a profile, how to compute a curve in the middle. So this is a mid-curve. So we have simplified the problem. So how does it look? Okay, given a black shape like this, Y shape, can you compute the middle red curve? Isn't it? The middle one is called as mid-curve now. And the original shape is profile. Is the problem simple and understood? So for L shape, black L shape, we should be able to compute Midcurve. Even this problem is little difficult. Imagine how would you write an algorithm for this? So what is the input? We are getting lines like this, the polygon lines, black lines. Can you write a function which will generate the red lines? Just give yourself a minute and imagine what would be the approaches. Now it is coming to computer science, right? Given lines, a little geometric computing, but still we are writing algorithm now. Got the problem? Now the problem from shapes, it has come to a profile problem. Given a set of lines, black lines, can you create or write a function to generate red lines? And it should work for any shape, like Y shape, L shape, there could be M shape, O shape, any such shape, not just letters, English letters, any such shape, having a thickness. Okay, this is the problem now. And there are many approaches for this. If you would have thought, I'll just briefly explain a very predominant 4 approaches. By the way, this research is going on for 50, 60 years, and still the problem is unsolved. And most of the algorithms are rule-based. One of the algorithms is, imagine that you have a circle here, and this circle is touching the profile, the blue profile, and the circle is traversed. The line that the center of the circle traverses, it's the midcurve, isn't it? It's a little approximate, not very correct, but you can imagine that's giving me a midcurve. The chordal axis transform is it meshes, it triangulates the shape and joins the middle points of the triangles. That's again the midcurve. Got the problem? Given a blue, can you calculate something in the middle? Another approach is thinning or offsetting. You go on offsetting the outer shape inside, and when you stop, you'll get a midcurve. Is this problem clear now? Given an outer shape, how can you calculate the middle shape, middle curve? And another approach is very similar. If 2 long lines are found, then offset one of them. That's also one approach. So there are quite a few approaches. And as you can see, this work is going on from 1967. So it's 50, 60 years old work now. By the way, I'm still in the domain. Towards the end, I'll talk about neural networks. So stay with me. Yeah, I'll wait here. By the way, this is my PhD research. This was my PhD research. And I did solve, to an extent, this problem with rule-based approach. Can you see? My approach was, given a shape, like this L shape on the left-hand side, I used to partition it. Partition at the corners. Then I take 2 shapes and compute the individual midcurves and join them together. So this is, on the right-hand side, is my implementation. This is my PhD work. From original left-hand side, the middle stage, and the right-hand. So you can see it is working for L. It is also working for T shape. By the way, we are not restricted to only English letters. You can see plus, minus, the cross, any shape having thickness, but in a polygonal shape, line shape. Even I did work on the curved shapes, but for simplicity, I'm showing linear shapes or line shapes. And you can see the results are coming okay. I'll wait here for a second and see if there are any questions. I don't see any questions. I'll go ahead with the presentation. Okay, so now this is the problem, and I worked on it in a rule-based manner. Given an input shape on the left, can I compute the middle curve or mid-curve. What were the limitations of my work? It was fully rule-based. And if a little different shape comes, if a curved shape comes or a different type of join comes, then we'll have to adjust the algorithm. And of course, this is not scalable. It won't work for any thin shape, right? So these were the limitations. So the idea came, can we use neural networks to learn this transformation? Isn't it the transformation from a 2D profile? Can I compute a 1D curve? It's actually a dimension reduction. 2D is thought of an area to curve, area to line. So this is a dimension reduction transformation. So can neural networks learn this transformation? But the big problem is, how do you feed geometry to neural networks? Although not like languages. Languages are converted to word vectors and then you feed them to machine learning or deep learning algorithms. But the geometry is a little tricky. Even though data is in numeric form, but there are quite a few challenges I'll talk about. Some of the challenges are, we need to have a lot of training data. And I had 20, 30 examples because it was a rule-based algorithm that was sufficient for me. But for me, I wanted a lot of samples because it is a neural network problem. So generating data was first problem. Lot of data. And it would be model. Once I have model, I'll have, what would be the input? All the lines or the points of the original shape. And what would be the output? Lines or the points of the output shape, isn't it? So this is how I want to build a neural network. So the goal is, given 2D closed shape, just pay attention to this slide, closed polygon, find its mid-curve or the middle red one that I had shown. So this is the problem. So from original aeroplane design, automobile design, chair design, we have come to a very manageable problem. But still, it is not solvable, but manageable problem. So what is input here? Set of points, so set of connected lines of the outer shape. It should be non-intersecting and many other things. And the output should be the middle one. I hope the problem is clear now. So given black shape, can I compute the red shape? It's almost like principal component analysis. Now we are coming to machine learning or deep learning domain slowly. It's actually a principal curve, right? So it's like a dimension reduction. The main point here is the mid curve should look very similar to the input shape. It should be homomorphic. It should represent the original shape. So if your original shape is Y-like, the mid curve should be Y-like. It should not be L. So that is the basic idea. So so as you can imagine, now this is a sequence to sequence problem. What is input? Set of lines, connected lines, isn't it? The black lines that I've shown. So that's a sequence. It has to be translated or transformed into sequence of lines which are red lines. So it's a sequence to sequence problem. Almost like machine translation. We have English sentence, which is set of words, and it's a French sentence, set of words. And the dimensions did not match, meaning there could be 5 English words and then 7 French words, isn't it? Similar to here, you can have 5, 6 input lines and 3, 4 output lines. So depending on the shape. So this is a sequence to sequence problem. It's not an auto encoder. So sequence to sequence problem, what do we generally use? We use encoder decoder networks. But it is not, of course, auto encoder because the input shape and output shape are not same. In auto encoder decoder, they are same. So it is encoder decoder, not auto encoder network. So what we typically use, we use RNNs, right? Encoder RNNs or encoder LSTMs and decoder RNNs or a decoder LSD. But one of the things that is needed, at least for implementable solution, like in Keras TensorFlow, we need to provide at least within a batch uh, a fixed size input. So in case of machine translation or language translation, what do? We do padding. So word vectors are there for each word, and then we have a padding vectors. Typically, say zeros, right? Adds are added, so that every input is of fixed size. Same is done for output decoder side also. But the problem in this situation, Midcurve situation, so we have points 1, 2, 3, 4, 5 points as inputs, the input shape, and output also 3, 4 points, right? So that's the thing. Can we pad with zeros? Actually, we cannot pad with zeros because zero itself is a valid geometric point, isn't it? So the shape will be little distorted. So padding is not possible. So that's the major problem I found while converting this geometry problem and feeding it to ready encoder decoder network, because padding is not possible. If we have a really variable network, meaning it's a batch size one only, and it varies, then we can think of doing real variable length in encoder decoder. But typically we send in batches, so padding is not possible. So then I thought of one more simplification. What would be a fixed size thing and still capture the variability? Can I have images of these shapes? Image of the outer polygon or outer shape, and image of the midcurve. Now then this becomes a fixed size image on the input and fixed size image on the output. So then it's possible to do machine learning and deep learning, isn't it? So we have converted a sequence to sequence problem to an image to image problem. Can we see the progression? Original problem was how to design shapes. Then the next level of problem was how to design a transformation or right transformation from input thin solid to mid surface. Then we changed it from how to compute a mid curve of a profile. That became a sequence to sequence problem. Now we are seeing as the sequence to sequence problem is not manageable because of the fixed size problem, it is converted to image translation problem. Now we can directly feed it to neural networks and then go ahead. So given a shape like this or image like this, can we generate an image like this, fixed size? Can we send image like this? Can we generate a image like this? So problem is image to image translation now. This is what it is. Now this is a solvable problem by neural networks. So what is the input? Given an input shape like this, input image like this, can I get output image like this? Given an input image like this, can I get an output image like this? Is problem clear? I'll again briefly stop here for a moment and then I'll go to neural networks. Now most of the things will be sort of familiar to you. I'll see if there are any questions. I don't see any questions. I'll go ahead with the presentation. By the way, can you just mention that this so far you have followed it a bit? And just one or two, if you can type in a chat window that if you could follow what has been mentioned so far. Okay. Yes, no problem. I'll share the screen again. So now this is image to image translation problem or transformation problem. Now things would be very familiar to all of you. So given shapes like this, I've just taken some English letters for now. Can you compute the midcurve? Now you can see the complexity. This is very simple shape. Simple, but there are joints, branches. Now these are concentric shapes. So this is what the problem we are working on. So given an original input shape, we'll have an encoder which will encode the input image, generate a latent representation or the contextual compressed representation, and the decoder. So again, it's an image to image translation. Given L shape like this is the input. My decoder should generate the midcurve. And so once the model is trained on hundreds of examples like this, these pairs, input and output, given any unseen shape, a thin shape, it should be able to compute the midcurve. So this is what it is. For deep learning, we obviously need just 20, 30 input shapes and their midcurves won't be sufficient. We want examples in hundreds. So we want input and output shapes, the outer profile and the midcurve in hundreds. How do you generate? So this is where data augmentation comes in the picture. We need a lot of variations actually. So this is the important part of this work, data preparation. So what was the input for me? The input points, the profile data, and the midcurve point. Given this data for one shape, right? Can you see the shape is getting close from 5,5 to 10,5, and then it's a closed polygon, and this is the midcurve. How many variations can I bring just for this shape? This is the outer profile shape. This is the input shape. How many can I bring in? Given a shape, how many samples can I generate? Ideally just one, but can I do some trick to populate multiple variations of this? And this is done by what is called as transformation, geometric transformations. So I'll show you some examples. Can I translate these shapes, both shapes, input and output, little bit, and generate 4 or 5 samples? Can I rotate bit, and then generate few more samples? Can I mirror both together? Can I mirror and translate? Can I mirror and rotate? So that's how I can generate variations of the same shape. So with this just three odd shapes, I could generate about 800 or 900 images just by translations. And if both input and output are translated similarly, that's actually correct input, right? But it's different. So this is how I've generated the data. I'll wait here for a second. Can you see? I've generated lots of inputs. And even these are inputs and these are outputs. Can you see? Lots of inputs, and I'll send them by pairs, right? Encoder and decoder, input and output shapes both sent together. Now we will show what the neural network was built for. It's a simple encoder-decoder network. Obviously, apart from that, we can try dense encoder decoder, convolutional encoder, and there are ready networks like pitch-to-pix. We've tried all of this, and I've created a GitHub repo, and all the code and this talk content is also shared on GitHub, open and free to all. So this is how encoder. Given an image, can I do simple encoder decoder image? This is the code. I've not shown every step, but this is how it is. I'll have encoding dimension, dense layer, and the output. This is the encoded part, decoded part. Although I've called it encoder decoder, autoencoder, it is both encoder and decoder, both together, and then you compile. By the way, what this binary cross entropy means, we are just showing, it's actually pixel to pixel classification. If you see, a pixel is either there or not. right, black or white. Similarly, in output, I'll do binary classification of each pixel, whether the pixel is there or not. Right? This is how the learning will happen, and this is how the implementation is done. By the way, source code for this, as I mentioned, is on GitHub. Towards it, I'll show you that repository also. And this is what I've got as results. Just simple encoder decoder. If you see a shape on the top, you can see its midcurve. These are predictions actually. And you can see at least spacing wise, its location wise, things are coming fine. And you can see a few problems as well. You can see some additional dots. These are false positives that have come. So, but the good part is, even with the simple encoder decoder network, I could get some midcurve. I will have to do post processing, or I will have to put what is called as a denoiser network little later and remove these additional things. But this is a very encouraging result for an original mechanical engineering machine design problem. We have sort of come to this, and if we solve this problem, it is currently unsolved because, as you can see, there are limitations. Once it is solved, we can take it back to machine design domain. Not very perfect, but encouraging results. And we will need people like you who are interested in this to work on this further, take it up as a research problem, and then move it further. By the way, all source code, even data, has been open sourced free. This is just my personal effort, but open to all. So we can do a lot of things, and then final the aim is to make a mid surface which can be used in machinery. So I'm towards the end of my talk now. So as we have seen, we had original geometry problem and we simplified it at various stages, got it into neural network and solved it. Right? So this is how deep learning has been applied using neural networks. So that's about it. And I'll close here and then I'll see if you have any questions. And in the meantime, I'll show you my GitHub repo also. It's called as Midcurve NN neural network. And I'll show you, paste you link here in the chat window also. This is the original problem. And quite a few things. And you can see source code here. So everything has been open sourced. Now I'll open it up for any problems. Or discussions. By the way, if you're interested in just having chat with me, you can send me a message on LinkedIn as well. I'll paste my LinkedIn profile. Ivy, if you can see if there are any questions, or else we can stop the session.
Hey Yogesh, can you hear me?
Yes, I can.
Yeah, so it seems like the audience here is pretty clear. They don't have any questions. Otherwise, well, and we'll pass it to them.
Yes, wonderful. Thanks for coming. I'm that this domain is a little different than, but at least sort of saw what an unknown domain can be converted to neural networks.
Okay, looks like it's all clear. The email is on the screen. Yeah, they can see it. And I think we can call it a day.
Okay.
Thank you so much, Yogesh.
Thanks, and bye.
All right, bye.